Okay, let me wait for a few minutes, then we can start. Okay.
Okay,
And do you have any specific doubt regarding this week lectures or last week class something?
I am checking the previous notes.
Okay. And I have told you that I will share this note and I will share it, but this note is quite advanced. Okay, means this course is also not basic statistical mechanics, although it is written, but uh, it's not a basic course. It's quite advanced course that I think you have understand. But problem is with this course, I think you have also failed because one thing is clear that it is not quite rigorous. It's for giving a overall idea, giving broad overview about the statistical mechanics. Okay, it's not very rigorous with full of derivation, not like that. Okay, so that's why this course is might be different from other regular courses, but still planning to do these derivations because from these totally theoretical classes, I can't formulate numerical question clearly. So for that, I have to first again do some derivation regarding these topics, and then I will solve the numerical questions. Some part of the of derivation probably you know because in last course also I have done this, but here I am planning to do it more rigorously because Bagdi sir is also teaching like that quite he's using those terms, those phrases, so I think that we can use, and it's not very difficult to understand, but it's okay, we'll do that. So for that today I'm planning that first we'll discuss some phase space. Do you have any idea about phase space?
No.
Okay, so but if you watch the lecture, then you'll see that there is a lots of description regarding this space, right?
Yes.
That mm, then we'll discuss some example of phase space. Obviously, after that we'll discuss that how one can implement how one can easily cross check this approach of statistical mechanics, not thermodynamics, statistical mechanics, to derive gas equation. Maxwell did that, but Maxwell did not do the statistical mechanics. Maxwell approach was also based on statistics, obviously, but in that case, the individual structure, molecule was not included. That's why, but we can do this. Yeah, it's very easy and very trivial. So I'll show that. I'll try to show that if it is possible. And then we'll discuss the canonical ensemble. Microcanonical I discussed yesterday in last class. Today also we first discuss the classification of ensembles and then we'll discuss microcanonical little bit because there is microcanonical is totally very trivial. Nothing is there. It's totally isolated system. But we can discuss after that the canonical one. So I plan like this. So we'll start. It's already 4:05. Okay. Now,
I was watching the lecture, but found this is too much advanced.
no, it's not advanced. It's basically, but this here is while also giving uh, lectures, but these are also doing like this means he just go here and there. He does not control yourself actually. those things are not yes, because you have not heard about before, that's why it's seeming advanced, but it's not advanced. It's actually um, if those words specifically, or those phrases can would be used after that course, after learning this. Okay, but for yes, for you it might be advanced, but it's not. It advanced because it's not in the right place. That's why. Otherwise, it is not there.
I have learned the ensemble and from the previous course, but this is also tough in this.
No, the ensemble idea will be same until you leave. Don't worry. Ensemble is ensemble. That's it. My voice is clear, right?
Yes,
Okay. Because today also the outside weather is not very good actually. So network can be interrupted in between. I don't know. Okay. So okay. So let me share my screen first. Okay. Is it visible?
yes,
Okay. Join documents. Okay. So now we can start. First, we'll discuss about the phase space I have mentioned. What do you mean? Discuss.
is it a topic of mathematics?
No, it is a topic of classical mechanics. It is a topic. Okay, just consider any particle, any particle. Okay, so you have studied that. I think you know about dependent variable and independent variable, right?
Yes,
Okay, so now to classify or to totally have okay to explain the motion of a particle, one particle I am saying, how many independent variable is needed?
three,
What are they?
three coordinates.
I'm saying variables. Okay, you are correct. Three coordinates is correct, but let's say one dimensional motion. Then the network is go to so this video can be off. Yes. Huh. So let's say for one coordinate, then it's a one dimensional motion. Let's say Then how many independent variable is required to explain the motion of the particle? Do you understand what is the independent variable means here? Means,
It is dependent on temperature.
no, I'm saying only one particle. So independent variable means you have to understand like that. If you know those variables, let's say x and y, two independent variables are. Um, if you know those variables, you can calculate all let's say acceleration, motion, means momentum, kinetic energy, potential, everything you can calculate just knowing those two independent variables.
So like time and distance.
Time and distance is correct. You can classify like this: time and distance. This is one option. Yes, if you know time and means position. Distance is correct, but yeah, it's better to say position and time. These two are independent variable. Correct. Also, you can write it like x and p. Correct. P is the momentum. Why? Because in p there is mv, and in v means x dot. There is a time also. So time can be manifested in momentum. So these two you can choose momentum and momentum and position, and time and position both. These two can be chosen as the independent variables. So now, if you plot, plot the motion of that particle with these two independent variable, along with these two independent variable, then that picture is called phase space. That space is called phase space. Nothing, it's not very difficult. Just let's say plot it. I am saying like this. I'm choosing, generally we choose x and p. Okay, so you can choose x and t, but if you know x and t, from there also you can calculate x and p. Nothing is there. So x in this direction, that p is. So at a initial time, let's say there is a position x and it has a velocity. It's a momentum. Some momentum it has. So then it will this point of this phase space. Phase space means this two-dimensional space here, because here two independent variables are there. So it will form a two-dimensional space. Okay. After some time, if this, just listen carefully, if let's say particle is moving at a fixed momentum, fixed velocity, then obviously its momentum will be conserved over time. So momentum will not change. But after some time, how time motion is appearing in the phase space, that I am explaining. So it's let's say time t equals to 0. After some time, momentum will not change. Momentum will remain constant, but position will be changed. So you will see this kind of motion. After some time, probably this. So it will be, the motion will be like this. Motion of the particle. Actually, particle is moving, but in this phase space, you will see like this. But if let's say momentum is also changing, then probably first point is there. After some time, you will get, after 1 second, probably particle is there. Then it is there. Then there. So you will see a trajectory over time. Particle is moving in the phase space like this. So particle is not,
It can go in negative direction also.
position and momentum can be, yes, momentum can also be negative. Yes, in that way you are correct. Obviously, it can go. So this is the actually particle is moving in our real world. But if you plot the motion of the particle each and time, you know the position and momentum of that particle, because these are independent variable. You have to know these values. Then you just point it out in the space, xp space. Then the point will move with time, and that trajectory is called the phase space trajectory. Okay, do you get it? Is it clear?
Yes.
It's easy. For two dimension, it's easy, because and you can also do it in x and t, but it's convenient to do it x and p, and each and every point is governing a particular time. Each and every time point time is changing, so it will be a new point in the phase space. Okay, this is the general
If we
definition.
do it x versus t, that it will be changed.
Say it again.
If we plot x versus t, then it will be change or it will be same.
Obviously, it will be changed because it's the y-axis momentum. Why t is not plotted? Because t is always changing. Na? T is a monotonically increasing function. T will not decrease. So t will be always increase. So from x and t plot, you will only have the notion of x. There is a p, but you have to calculate it. It is not explicitly in front of your eyes. So that's why
And
you
if
have
we plot x versus v,
that is same. X versus v and p same. Just there will be divided by mass. E is nothing but mp. Right? That's the reason. So generally we plot with x and v, x and p, position and momentum. Now it's one
So
dimension.
we don't consider mass because it's a constant, right?
But if it is a relativistic particle, then you have to consider p. Na? Instead of v, it's better to consider p. If it is a non-relativistic particle, then it does not matter. E and V will carry the same feelings or motion. But when it's a relativistic particle, because in quantum mechanics, in classical mechanics it's okay, but in quantum mechanics you are talking about electrons. So in that case, you have to consider the momentum. It's better to consider momentum. But in our case, for timing, you can choose the velocity, position and velocity. But you have to remind that this is for one dimension only. If it is three dimension, then you can't plot like this. In three dimension, how many independent variable will be there?
or
Why?
three dimension and one time.
No, in terms of phase space, I'm saying. You are correct. Three positions, x1, x2, x3, or it's better to write q1, q2, q3, in three dimension. Time we are not taking because time will be anyway uh, implemented in the phase space by changing the points. But there will be again P1, P2, P3, na? That is important.
Then three variable.
Six variable. Six independent variables are needed. Three position, three momentum. Is it clear?
Momentum in
Oh,
every
so momentum
direction.
is split across the three axes.
Three axis, yes. Because when particle
Oh,
is moving in three dimension, it has arbitrary momentum, right? And you can break that momentum in three component, px, py, and pz. In general, I am writing it p1, p2, pa. It's actually px, py, and pz. And it is qx, qy, qz. You can write it. So three,
Every momentum is independent.
yes,
In x
absolutely.
direction, the momentum of y direction is zero.
And zero? Yes. If particle is moving around only x direction, then obviously py and pz is zero. But you don't know. It's a free particle. It can move any direction, right? So it can x, y, qx, qy, qz. It can be anything, and it is changing. It is not fixed. At a particular point, maybe the px is zero. After some time, py is zero. Let's say you have a one particle and that is moving in a room. So px, py, pz, qx, qy, qz, everything is changing. That is important, no? So these things are coordinate and these things are momentum components. So these three total six independent variable will be there. Now, can you plot it? For one dimension motion, you can plot it. But let's say for a three-dimensional motion, can you plot it?
No.
No, because how many coordinates here x and p, but you need six coordinates. Means three for
Yes.
x, three for y. That you can't draw actually. Up, we can draw up to three. That's it. And if you consider the negative axis, then six. But here it's not negative axis. It's actually three variable, three, six variables. So you can't draw six. dimensional phase space. It's called a six-dimensional phase space. Six-dimensional phase space. So what to do now then? Then basically it is actually plotting like this: Qj, Pj, or it is actually a set of Q1, Q or Qx, Qi, Qz, whatever you want to write, and it is a set of P1, P2, P3. Then you can, it is just a hypothetical phase space. Okay, so basically uh, Qj, this is a set of all positions. So it is Q1, Q2, Q3, and Pj is the set of all momentum P1, P2, P3. Then you can draw the phase space. Now each point in the phase space right now, let's say this point here, it cuts here, right? It does not signify one particular value because it is now, it's a not a axis, it's actually set of axes, right? So it will signify three values. Okay, so each point of this axis you have to define like that. Each point will signify three values, and this point also signifies three values, and from there you can draw it like that. It's not very realistic thing. It's just for our convenient. It's six-dimensional phase
What is the
space.
value of the coordinate point?
You don't have any particular value. You will say, let's say if it is one, then you will say it's set one set q1 set, let's say q. After some time it's q prime. After sometimes it changes. No, it actually depends on time. It, let's say it is
I
q.
am seeing the value of the point,
You can't mention a particular value of that point.
like Qj, comma Pj.
That you can write, because yes, for each point you can write in general qj comma pj. But qj has three quantities. Pj has also three quantities. So when you write qj comma pj, it essentially means q1, q2, q3, p1, p2, p3. You can think like it's just for a shorthand notation. Okay,
So
that's why we
every
have.
time particle has to move in a particular direction.
Yes, obviously. So again,
So,
It
so
cannot
if
move
you
in two
write
directions.
Qj and PJ, Qj comma PJ, we are just saying we take all the momentum and
all
stuff,
momentum and
right?
position, yes, position and momentum
Ah,
components, all
okay.
we have breakdown in components. So it's for one particle, keep in mind. So for one particle, if you consider three dimension, there will be six-dimensional phase space. Now if you have n particle, generally you have n particle, not one particle. So for n particle, the phase space will be, what will be the dimension of phase space? For each particle there is six, so it is six n dimensional phase space. So it's very non-trivial thing. Six n dimensional phase space it's called. So what are six and nine? But how you can write it? Again, now you can draw it just like the previous one.
NQJ, NPJ.
No, it's just PJQJ.
Yes, the J value is 1 to n.
Yes. So here QJ is basically set of Q1 number of particles. How many particles you have? Q2A.
So it's like difficult to quantify, right?
It's okay. It's better to write like this actually. One, two, three, up to 3n. right? For each particle, there will be three coordinates, no? Q1, Q2, Q3 for one particle. For second particle, it will be another three. So for n particle, there will be three n coordinates and three n momentums. So total 6n dimensional phase space. So again, here you can define a trajectory like this. And this trajectory means it's actually time is changing. Each and every time it generates one point. If you change time, it's a new point. Another time, it's a new point. Okay. And it is called totally hypothetical space. And this hypothetical space is called phase space. So is it clear or not?
Yes, sir.
And this figure you have, I think, shown in the class, right? QJ, PJ, this kind of figure. But if you think
Yes.
actually what is this each point, let's say these points, what does it actually means? Can you guess it? You have what? You have a, let's say, box with n particle, right? For n particle, there are six-dimensional phase space. Okay. And each and every time the point of phase space is changing. So what does the phase space point actually signifies?
Change of velocity.
No, no. Yes, change of velocity or position is correct. But actually, what does it mean? New point, let's say this is point A, this is point B, this is C, D. So system is changing or not? System is not changing.
Changing.
No, system is n particle system. N particle you have just taken in a box. Macro
Yes.
state is not changing, but it is each and every new micro state. You get
Oh,
it?
okay, okay. Oh, each point is a state.
Each point is a micro state because orientation is changing, na? It's a new combination of velocity and position.
Yes.
So each and every point is a new micro state. Macro state is same. Macro state is this. You have keep this. But each and every time this distribution is changing. It's now new distribution. After some time, it's a new distribution. When distribution changing, this QJ and PJ changing, and it's a new point in the phase space. That's why each and every point and each and every time a new point in the phase space is generating, and you will see a trajectory over time. Okay, this is the
Yes.
main thing. This is the phase space. That's why phase space is important. Okay, now we can discuss more about phase space, but it's okay. It's enough. But how you can, if it is a classical motion, classical particle, then this QJ and PJ can be calculated using this formula. You, I think, know. This is called Hamilton's equation, right? Using this
Yes.
Hamilton equation for a particular time, you can calculate QJ and PJ. Okay, that's not important. Okay. I'm not going into rigorous calculation. I'm just giving you the idea because these things are often used in the class. But my teacher is assuming these things are known to people, but it's not actually because I have also learned this phase space in my MSc thing. In classical mechanics, it's because we have not studied classical mechanics thoroughly. That's why it's the problem. In classical mechanics, when you study the harmonic oscillator, then this phase space is discussed elaborately. That I will discuss right now. You will see. Okay. Okay, before that, these all things are microstate, right? Now, when you want to
Yes.
calculate one particular property, any property, let's say x, then you know how to calculate time average, that thing we have discussed. You need an infinite number of points that, let's say, up t time, 0 to t, capital T time, or tau time, there is an infinite number of
Integration
points
zero to t.
generated. Then you have to integrate from 0 to tau, and this x, this property is changing over time, so it's just dt, or better you can write it x, which is a function of t, dt. It may be position also. For position, you can think Each and every time this position is changing, each and every microstate, the position is different. Here position means the total position. So then you have to just integrate over time and you have to divide by time. And this is called the time average property. But you know, this is not possible to calculate. That's why we need the ensemble average later.
Ensemble average.
Just now you can visualize what does ensemble do. Here you have kept the macro state constant. You are not doing anything with the macro state. You have just taken n particles and kept that n particle in a box. Now that macro state is fixed, but each and every time the micro state is changing because new orientation, new combination of xj, qj and pj is occurring, and that's why it's a new point in the phase space and the trajectory moves, right? When time is, actually this definition is correct, you have to write it. This tau should be tends to infinity. This should be huge time scale. Then it will be a more difficult trajectory, let's say something like that. Any trajectory can be done if time is large. Some trajectory is generating. This is the phase called phase-space trajectory. E Now each and every point is actually not drawn like this because you know each and every point is basically considering 6 data. You choose one point, it has 3 momentum, 3 coordinate. It has a 6 data, so it actually like this.
If it is a 3D particle.
Particle is 1D motion in 3D.
Yes.
Particle, most particle dimension, what does it? So it is like that. It's a phase trajectory, but for our convenient, we are drawing like the simple thing. Just you have to keep in mind that it's not a two-dimensional thing, it's a 6-dimensional thing. So each and every point for one particle, it has a 6 point, but you are considering 6-dimensional. So 6-dimensional means each and every point, how many uh, in values are there? It has how many values? 6 number of values, right?
It's a number value.
So that's why it actually written like drawn like this. But drawing like this is hectic job, so I'm not doing that. So it's just I'm drawing like simple thing, but you have to keep in mind one point is signifying 6 values. Okay, so let's say it's a phase space trajectory. Now what does ensemble picture do? Ensemble picture do means you have to generate all these points, correct? But you are not changing
Yes.
time. You are not changing time. Let's say time is 10 to the power 10. It's a huge time. So each and every time you have a particular point. So let's say here 10 to the power 10 number of points has been generated and you have connected those points to create this trajectory. Now in ensemble picture, you are not changing time. That's a particular time. You have fixed the particular time. But you have made 10 to the power 10 number of copies of that macro state. So you had one. First, what is this? First scenario is you have a one macro state and micro state is generating over time. Time is changing. But now you have a fixed time and you have 10 to the power 10 number of macro state. You have make copies. So each and every copies there will be new micro state. So this hypothesis is time should be large enough and this number of micro states should be large enough so that all points generated by the time evolution should be generated by this ensemble thing. That's the point. You have to generate all these points now. Then it will be the same thing. Then you calculate the average. That average will be ensemble average, and then ensemble average will mimic the time average. This is the whole thing. Okay, why this thing is ensemble average is important? Is it clear? It should be clear.
Yes, because we cannot consider all the possibilities.
Because time changing you can't calculate. But when you
Yes.
fix the time, at a fixed time, you are generating all possible microstate by generating that huge number of macrostate, then it's clear, right? Okay. Okay. So now this is the then ensemble, but that I will do later. I will calculate the canonical ensemble one. That's these things in this class or next class. I don't know, but I will do. Canonical ensemble you should understand in detail because microcanonical ensemble is easy and that is not realistic. And grand canonical one is very difficult. So canonical one is important. But interestingly, at a particular point, or you can say in general, you can think, uh, okay, this will I can say later, but at a particular what happens, canonical, microcanonical, and grand canonical, all three ensemble actually emerges to a same ensemble picture. Okay, okay, that things I'm not discussing here. Okay, but it's better now. We should discuss an example of phase space. Okay, that I will do. That space of harmonic oscillator.
All ensemble are same.
Our ensemble pictures will be same. Means if you let's say uh, you have a system, any system, you are classifying the system as a canonical ensemble, means NBT. That things I will
Yes,
do
NVT.
later. Then you will, after considering canonical ensemble, you will calculate, let's say, internal energy or entropy or enthalpy. Okay. If you choose the grand canonical one, you will have the same value. If you choose the microcanonical one, you will have the same value after some limit. That is important. That I will say. That is called thermodynamic limit.
At one it's NVT constant, one NVE, one mu VT. So
But
how?
all pictures will be emerges to a same thing. Means canonical, microcanonical, and grand canonical will be same after some limit. That is important. That is important.
Can we calculate the limit?
Can we calculate the limit? Not explicitly, but you will see how these pictures are becoming same. That you will definitely see.
Okay.
Okay. Harmonic oscillator. So let's take an example of harmonic oscillator to just understand the phase space better. So you know the motion of harmonic oscillator. Okay, this is the motion of harmonic oscillator. It will oscillate. What is the energy of harmonic oscillator? H means total energy, means kinetic energy and potential energy, sum of. It is kinetic energy. What is the kinetic energy? Half mv square, right?
Yes.
And what is the potential energy?
Kx
Half
square.
kx square. Correct. But this is for one dimension.
Yes.
Okay, but still we can write it in general q. One q value will be there because we are using q and p notation. That's why I'm writing q. You don't know whether it is x direction, y direction, z direction, but it's okay. And it can be written as p square by 2m. You can write it. Okay, is it okay?
Yes.
Okay. And this is the energy, total energy. You can write it as h or e, whatever it is. So you can write it q square see. Can you write it?
Yes.
So which equation is this? Which geometrical shape? Equation of which geometrical shape?
Parabola.
No, ellipse.
Sorry, ellipse. X square by a square plus y square equal to 1.
Yes. This is equation of ellipse. So here x and y is q and p. That's what we needed. We have to plot in terms of q and p, right?
Yes.
That's our independent variables. Okay. So it will be a ellipse. We draw a different color. Okay. Okay. And you see, there are two things: semi-major axis and semi-minor axis. This is
Q is
our
the semi-major axis.
this is semi-major axis, which is root over this, and this is our semi-minor axis, which is root over 2me. So let me draw it a bigger so that I can. So here, here it is q, here it is p. So this distance, this is actually our b, and this is our actually a. Semi-major axis, semi-minor axis. Okay. So now, at a particular energy, this will be the phase space. Means each and every time is changing, so each point will be generated and it will form a ellipse. After some time, again it return to the same point. Periodic motion you will see. So this is the phase space. It's easy to understand because it's just a two-dimensional phase space, right?
The value of B is equal to P.
Value of
B, that is equal to root 2AB, is equal to P.
no, that will equal for this point only. Let's say for
Okay.
this any point here, this is P and this is Q. That's the thing, na. Time is changing, it is oscillating means what? Time is changing. Let's say you have started from here, that point. Here momentum is zero, right? Momentum is
Yes.
zero, but there is a Q. Means you are starting from here, okay? When it reaches here position is zero, but there is a momentum. Let's say here,
Potential energy is zero there.
then in this point, this momentum is again zero, but position is negative. So this point, and again it will return here. So again this point. So you see this motion.
Yes.
This motion is generated, right? So each and between points, let's say it's here, then this point maybe. So each and every time, new point will be generated, and if you connect those points, you will have this phase space picture. So this is the definition of phase space picture. Now I think it's clear. But if
Yes.
you remember, for simple harmonic oscillator,
Oh, so is this ellipse the ensemble thing?
no, it's not ensemble picture, it's time.
Oh,
Time is changing, that's why each and every point is generating. Here ensemble is not needed because it's just a two variable thing. And it's a periodic motion even. So when it's a periodic motion, you can calculate anything
Yes.
because you have a equation, right? But if it is a free variable, then it is very difficult. If it's, let's say, it's free particle, you can't do it. You have to do ensemble picture. So, but here one thing is this E is constant. E can't be changed. You know, there are two
Yes.
clauses, right? Uh, one is decreased. Forgot actually like this, and another one is increased like this, so that the overall energy remains fixed. Correct?
At all point of the time.
Huh. That's why energy is invariant. So this plot is for a one curve. This E is constant. E is not changing. For each and every point, E is same. But if the energy is different, then there will be a new curve. This is a new curve. Let's say this energy is E prime. That's it. And this difference of energy is daily one thing like that. Okay. But I'm not going the fluctuation. This is called flux. Okay, this is okay. Oof, okay, yes. Now, this phase space I mentioned, I discussed everything. This is based on a classical particle. Correct? Particle is classical particle. I have never mentioned any quantumness, anything, right?
Yes.
But let's say if the particle is quantum particle, then what thing will change? It's not a classical particle. You have n number of quantum particles.
Its mass will be changed.
No, I mass keeping constant. Electron, let's say electron. Electron, you can consider electron as a classical particle first.
Oh,
This
so
is not
its
classical.
position and that won't be known, right? That's the thing.
Position and momentum.
Position moment.
There is uncertainty between position and momentum, correct?
Cannot be calculated simultaneously.
Simultaneously. So there will be uncertainty. So previously, you can calculate a particular point in a phase space, which governs 3n number of position, 3n number of momentums. But here you can't. There, there will be a uncertainty. So basically, there will be a uncertainty around this point. So you can have the particle around this point. This is the region. What will be that area of that uh, square, or we can think what is the region, in the area of this region that you can calculate. How? What is the uncertainty relation? That del
Into
p,
del P greater than equals to h by 4 pi.
and saying the lower limit h cross, correct? H cross by 2,
H
more
goes by 2.
to be more precise. Well, in the order of h cross, it means 10 to the 34. That's the main thing. Okay. So if it is a one-dimensional particle, let's say, first understand one-dimensional, is q and p. One dimension, one particle moving in one particle is moving in one dimension. One particle and moving one dimensional. Then this amount of uncertainty is there. So you are saying this is q, but there is uncertainty between q and p, right?
Yes.
That uncertainty is h cross. This is h cross, and there will be another uncertainty in p as well. So you can have the particle around this region, around this point, not exactly at that
So
point due to
what is
uncertainty.
the shape of the region?
In general, we consider square. Okay, and this square area of the square is
H cross square.
h cross square. This is the shape. Yes, no, not square. It's h cross. I think yes, h cross because
Why?
uncertainty both
Uncertainty
in
in both.
in no, not in both x and p is not h cross. Total uncertainty is h cross, right?
Yes.
You can't make uncertainty is x also h cross, p also h cross. Then it will be h cross square. That is not true. Uncertainty is h cross. So for each point, each particle, you will have uncertainty of h cross. Now, let's say it is a three-dimensional thing. Then particle the uncertainty will be h to the power n, and for a 3n dimensional thing, it will be h cross to the power 3n. So this is the uncertainty, and it is very important. Why? H cross may be a small number, but if n is very large enough, then it may be significant. So this amount of uncertainty you will see when you consider a quantum mechanical particle. Okay, so let's say that's why total volume will be distributed because before you because what happens, you are considering now after some time one point is there, let's say, then another point is there, trajectory was forming, but now you can't do. If one point is there, after some time the point may not be here because uncertainty is there. No, it should be outside. So it will form, let's say, a cloud like thing. You have to it's better to draw like this. This will be a point. and this is changing over time. So you can understand for quantum mechanics, these things will be very complicated. For classical particle also, this is not very trivial. But when you consider a quantum mechanical particle, it has a certainly it has an uncertainty, and due to that uncertainty, the phase space picture become also very much complicated. That's the thing.
When the n is low, can I neglect the uncertainty?
Obviously, you are not neglecting uncertainty. It's actually cumulative effect is neglected. Uncertainty is there.
What?
Cumulative effect is neglected, right?
Yes.
That's the thing. Uncertainty is there. For each and every particle, H cross uncertainty is there. Okay. But not only the uncertainty, when you are considering it's a quantum mechanical particle, na, this every laws will be different. You have seen that in previous courses. When it's a quantum mechanical particle, the distribution changes. It will be either bosonic particle or fermionic particle.
Yes.
So that microstate, when you calculate the partition function later, that will be different. So everything will be different. So that is not the thing.
Their spin will be different.
Spin will be additionally appeared because spin is a feature of quantum mechanics. In classical mechanics, you don't have spin. Do you have spin in classical mechanics?
No.
It's a and if you remember when you solve the hydrogen atom from Schrodinger equation, do you have solved that
Yes, a little bit.
little bit? So when you solve it totally, you will see you will have quantum numbers n, l, and p, but
Yes.
s will not be there. You can't calculate s quantum number will not be there.
From Schrodinger equation, it is not getted.
No, from Schrodinger equation you can't get the s. So how you can get s? You have to do relativistic quantum mechanics. Instead of Schrodinger equation, you have to consider Dirac equation. Then you can have it. If you do
Yes.
the calculation using the Dirac equation, then finally you will have the spin. Spin will appear. Okay. Okay. So now, uh, what will be the volume of phase space? What will be the volume of total volume of phase space? Let's say it's gamma. You can choose. I'm just saying it's gamma. Now I'm not doing quantum, right? I'm doing classical. But in classical, around this space, it's not only one point, correct? It's a huge number of points. Six and
Yes.
number of points are there. Information are there. Six and number of not points, information are there. So, uh, should I say these things? Okay, it's not very difficult. I can discuss. Okay, so you can define a density actually. That is called phase space density, which is called rho uj pj, and at a particular time, each and every time the point is changing. So rho qj pj and t is called the phase space density. Okay, so you can calculate how many points are there. That's the thing. Clear? It's not clear, I think, right?
Yes.
Let me explain it again. So each and every point, there is a density. Okay, it is clear because there is not a single point.
Yes.
Okay, so these enormous number of ensemble due to when you calculate the ensemble picture, it is in case of time picture is okay, but when you calculate the ensemble picture, you have to calculate it what happens in ensemble? There is an enormous number of points, right? You have having various number of microstate. So
Yes.
it will have a collective number of points. So that's why you will have these things for ensemble picture. Ensemble picture, I'm saying, not time picture. Ensemble picture. For ensemble picture, at a particular time, when you calculating the ensemble picture, you are not changing time. At a particular time, when you calculate ensemble, obviously there will be huge number of value we'll get. Yeah, let's say it like this. So there will be a density that is called rho uj pj t. For each means you can have different value when we do canonical ensemble, then you will understand it's very practically actually. Oh, how I can explain it. Okay. Last day we discussed the huge number of ensemble. Now you are calculating energy. Energy equal to 10. So it's not guaranteed that you will have the value of energy 10 only once. You have infinite number of copies, right?
Yes.
So with same energy, we will have more than one. Let's say there are 50 copies we having energy equal to 10. That is possible.
Yes.
So similarly, having here, when you have the ensemble picture, having same value qj, pj, and t, there may be t may be different, but t is there for ensemble picture. T is same, so you are not changing t. But having same qj and pj, many points you will get, not one point.
Yes.
So that is the density. How many points you are getting?
Oh,
Okay. So that's the okay. These things I'm not going to wait. After doing canonical ensemble, these things will be anyway clear. For timing in time average, it's like this. That is called density of the phase space when you do ensemble average. But time average, there is no one. The time average, there is a 1 point. But if you are doing n number of particles, then 1 point will signify 6n values. And if it is a quantum mechanical particle, then obviously there will be an uncertainty of the dimension h to the power 3n. That's it.
For
Okay.
time average, there is no density.
No. Time average, time is changing now.
Yes.
That's why. You will have the same qj
so
pj again.
I just have a doubt.
Ah,
Is this density thing how many particles have such and such position and such momentum at a
this is
particular
actually
time?
particle density.
Oh,
Means
okay.
at a particular point, how many particles you are having like that. So when you multiply it with the volume, you will have the total particle. Okay, I will come into that point after doing canonical ensemble, don't worry. This is for timing, it's quite abstract actually. Um, in one dimension box, probably these kind of things are there, 2 dimension or 3 dimension box. Yes, 3 dimension box, probably you have studied these things, right? With same energy, there may be more than one microstate, one energy state, right? Same energy but different state. That is the density of state. I don't know whether you
Oh,
know
City box.
these things. Uh, Let me find out more. Something. Let's say you have huge number of particles. Okay, and you are calculating huge number of particles. You are calculating the not particle. Forget it. You have huge number of humans. So now you are calculating the masses. So there will be particle density, na? Human density for each and every masses. Is it
yes.
understandable? Density does not means the volume density always or mass density is mass by volume, correct? Charge density is charge by volume. We generally consider density means mass density, mass by volume. That is not true here. It is a particle density means number of particle per volume. That's the case. This is called particle density. Okay, these things is quite difficult. After doing canonical ensemble, I will do that. And if you calculate it from this density, calculate this density, then you can uh, have a analytical expression for ensemble average and the our time average. Time average is already shown to you. Ensemble average equation I will show you. We have a general definition. After when we do the canonical ensemble, we'll elaborately calculate the ensemble averages and ensemble quantities. Everything will calculate. Okay. Okay, I think this is enough for this phase space. Now phase space is clear, right? Nothing should not be there. If there is any confusion
Yes.
regarding phase space, you can ask. Now we can start referring. Phase space will be useful always. If you read statistical mechanics later, always phase space is there. Not only statistical mechanics, when we do the molecular dynamics, if you study, because there when there are a number of molecules is used, their phase space is very important. Okay. So now what we can do? Yes, this is very interesting. I guess it will be so. Yes, yes. Hmm. Okay, from this thermodynamic, from this statistical mechanics, you can calculate the um, ideal gas equation. That I will say. Mhm. That one thing is needed. So, 1 minute. Vertical ensemble is start that actually. Okay, and before that, I will discuss the types of ensemble. Then we will do that because before doing canonical ensemble, everything can be difficult. Seems difficult. Okay, types of ensemble. Let's say you have now in the importance of ensemble is clear, I guess. Now, how the ensemble that is important because let's say if it is a isolated, first you have to understand the macro state. What is the macro state? My voice is clear.
Yes.
Uh,
Okay, so macro state means the system state, right? Let's say this is a macroscopic system. Macroscopic system. Here it is again very important. So how many variables needed to explain a macroscopic system?
PBT.
PVT is correct. It may be PVT. It may be NVT. It may be NVE. Anything can be right. But you need a three independent variable. You need three independent variable to describe a macroscopic system. Remaining constant, that is important. Okay, I'm not uh, maybe it may be confusing. Let me say it in a different way. So these things you have studied. How many types of systems are there in thermodynamics? How many types of system you have studied?
Open, closed, isolated.
Exactly. Three types of system are there. Isolated, close and open. Isolated system means it will exchange nothing, no energy, no particle, right? Closed system exchange energy but not particle, and open exchange both. Okay, so when you have an isolated system, the macroscopic system is an isolated system. It's not interacting with the surrounding. Isolated means like that it is not interacting with surrounding. When it is not interacting with surrounding, then only the energy and number of particle will not be exchanged. So for isolated system, which parameters will remain constant for that system?
Energy,
Energy and
temperature.
temperature will be constant. Is there any notion of temperature?
No.
Temperature will not be constant. Energy will be constant because no energy is being exchanged.
Number of particle is constant.
Number of particle, and anyway the volume is constant.
Yes.
So for a macroscopic system, NVE, these three important things, all three are constant. So now when you make the ensemble of these three pictures of this, you have to make a large number of copies. Let me draw it. So let's say there are huge number of copies. So this is one microstate. These are copies of macrostate. Just understand this same macrostate. I am just copying here. This all same copy of the macrostate. All NVE is fixed. Okay, NVE for all cases. NVE are fixed. Like that. Okay. This is called microcanonical ensemble. This is micro because you have having infinite number of copies. I think it is clear, right?
Yes.
You are having just you are making infinite number of copies, but each and every copy is the macro state is same. It's correct because you are copying that, so macro state must be same, but micro states are changing. So it's giving you huge number of micro states. That's the
Can you please explain that again?
okay. So what is the macro state? Macro state is this state, correct? This is the macro state. This is not change. You have only this is the real state you have. You have a box filled with a gas molecule, let's say, and it's an isolated system. It's not interacting with surrounding. So number of particle will remain same, volume will remain same, and energy will remain same. So NVE, all three will be remain same. So this is what macro state. Now macro state, when in time average picture, what we have studied that in macro state, these molecules have a particular orientation. Correct? It's a particular orientation. After some time, it will be a new orientation. After some time, it will be a new orientation. So new orientation means new microstate. Microstate means the internal orientation, microscopic orientation of the particles. So that's a new orientation. So that's why each and every point will be generated when time is changing, and every point will signifying to a new microstate. That was a time average picture. But in ensemble, we are also generating microstate, but not by changing time. Time is t. Time is remain constant. At a particular time, you are copying all the copying this macroscopic state. You are copying infinite times. Infinite macroscopic macroscopic states you are copying. But each and every copy, microstate should not be same. Here the distribution is something. Let me draw. Remove it.
Oh, so it's like how many unique ways particles can be arranged in a fixed NVE system, right?
Uh, yes, that's true, but you don't need to understand like in that way. It's very difficult. Just to understand in that volume, this space, in this system, the particles are moving, right? So at a particular time, particle has a particular position and momentum. That's a particular orientation. I'm saying. After some time, the position, momentum, all will be changed now. So that's a new
Okay.
orientation. That's a new microstate. In a room, let's say there are six people are moving, walking in a room. So at for a particular instance, that is a microstate. After some instance, the position and momentum will be changed. That's a new microstate. So in that way, microstates are generating. That's a time average picture. So you have to collect all the microstates and you have to average out. Then you will have the time average quantities. But in ensemble, you are not changing time. At a particular time, you freeze it. You have taken the room. 10 people are there. They are moving. It's correct. You are now copying this room. Let's say 10,000 copies or more than that. Infinite number of copies you have made. Now, at a particular time, you freeze the time and you open the room and you see each and every room. The distribution of that 10 humans are different, right? So that each and every room will be will signify a microstate. Just you are generating the microstate not by changing time, just by copying the room. That's the beauty of ensemble. That's called ensemble. So here you have this lots of number of copies. Here, let's say this is one orientation. Here another orientation. Here let's another orientation. For each and every macro state, each copy, the orientations are different. So you have to make infinite number of copies so that all orientation can be occurred for time average also. In time average case
NV is
also,
constant or not?
huh?
NVE is constant for the microstate also or not?
Yes, obviously for macro state NV is constant, so microstate will be, but orientation is not constant. Orientation is changing. Position and momentum is changing.
Can I say pressure is changing?
No, any macroscopic quantity is not changing. You are saying
NV is
is not
constant only.
E is not changing, is correct, but for each and every particle, EI, that is changing. What is not changing? E average is not changing.
Yes.
That I was saying that there will be a fluctuation. If you see, let's say for this picture also, with time, mainly it's with time, E is changing, but E average is remaining constant. But there is a fluctuation around E, like this. It's not pure constant because particles have. This means the average of all the internal energies. Not that we get na. We are we measure. We can't measure, but we having a uh, bulk picture means that is the average thing. Average internal energy. E means in all thermodynamics, classical thermodynamics, that ES, H, everything you have studied, that's all the average thing. That's a macroscopic thing, right? Means you have taken all energy of that particle and you have average out. That's the thing. Here also you have to do that. So you have to calculate average energy of all of all microstate, and then you have to average it out and to calculate the E average.
It is okay, but I am saying for the macrostate only NVE is constant.
NVE is constant.
So other anything can change.
No, it's isolated system. How it can be changed? Just
The
understand.
NV only matters for the whole system, right? Each particle will have its own energy and stuff. That's the
Means
average,
when it's
right?
not interacting with surrounding, any property will not be changed. Correct. Pressure,
Yes.
how pressure is changed. If you remember, either you have to make pressure from outside, then you will change, or if the inside pressure is greater than outside, you have to interact with the surrounding outside. Otherwise, pressure will not be changed. Okay. Pressure will remain constant. No, everything will, for isolated system, nothing will be changed. It will be as
Anything
it
that is
is.
interchanging between the microstates.
Huh?
Any property that is interchanging between the microstates.
No. All my these all copies, not these are all copies of macrostate. No, these are separated by rigid walls. These walls are rigid. Means no particle is changing, no energy is changing between
So
the
only
two.
the molecular arrangement is different from one
Molecular
ensemble to
arrangement
another.
is different, yes. Internal molecular arrangements are different.
Only that is.
That's why it's all a new microstate. Same macrostate, but new microstate. Different microstate. That's why if you see the EI means energy of each and every particle, that is changing. That I'm not saying that is not changing. If you see each one system here, these particles energy is changing, but you have to average out it. Then you
The
will
average
have
is
the,
constant.
that's the thing. Finally, we have to calculate that. We will calculate for canonical ensemble later. For microcanonical, you have nothing to calculate because for all pictures, E is same, correct? So when E is same, so only thing you can calculate that is entropy. Entropy will be Kb ln omega. This is the entropy for this microcanonical ensemble. Means the system entropy of the system, isolated system. This is the Kb ln omega. Okay,
Yes.
omega is, what is omega?
Number of microstates.
Okay, so you have to calculate the number of microstate, and then you can calculate the S. Okay. But this microstate is not this. Okay, how how these microstates are generated? These microstates are generated due to the orientation of the molecules, right? Or the particles inside the system. That I will now show some example, then it will be clear how this microstate can be calculated. Okay, so let us take some example.
S is entropy, right?
Entropy,
Just clarifying.
entropy, entropy. And this formula is for only the our microcanonical ensemble. If it is not, its general formula is minus pi ln sum over. This is the general formula. Pi is the probability of having a microstate, and you have to sum
Minus
over
nr summation pi ln pi.
minus
Nr.
a n.
Yes.
No, a n, not a n. It's kb. kb. kb you can write in terms of it in any way. But in import kb is not important. Important is pi ln pi. E is the probability, and this is called Gibbs energy for Gibbs entropy formula. Okay. So ensemble is now okay. It's microcanonical. Okay, these things we will discuss: microcanonical, canonical, canonical, all three things. But first we will discuss other ensemble. If it is isolated, then it is microcanonical. Okay. Now, if your system is a closed system, That means it can exchange energy with surrounding, but not the particle, correct?
Yes.
Then if you make this in huge number of copies, then the particle is this wall is not rigid. This can exchange energy. So it is a
Yes.
uh, capacitive wall. Capacitive, what it said actually? Capacitive note. What is the term? Conductive wall. Okay. The energy can be exchanged. So then this picture is called microcanonical ensemble. This ensemble will be microcanonical ensemble. Now in microcanonical ensemble, what will be the constant property of this macrostate? What what things are constant?
NVT.
NVT. Because N and V is anyway constant. Now T energy is changing within the system, within the surrounding, but essentially you have connected overall system with a thermal bath. Don't think in difficult way. Thermal bath means you can consider our environment or nature. If you have just if you kept a system with n number of particles in nature, after some time it will be equilibrated with the surrounding, right? And the temperature of that bath of that system will be same with the bath. Bath means the surrounding. So if the temperature of the bath is T, the temperature of the uh, each and every macro state, this macro state is T. And this is the same macro state. You are just copying macro state. Micro state will be different. So the NVT will be the same. Okay.
All microstate can interchange the energy between them.
Exactly. Now all microstate can interchange the energy between them. This is now interchangeable. This energy now interchangeable. That's why energy is not fixed, right? Otherwise energy would be fixed.
And molecular arrangement is also changing.
That's why it's a new microstate. Obviously, molecular orientation is changing. Okay. So walls are heat conducting.
If energy is changing, then macrostate is also changing.
No, just understand. Now the macrostate is defined by NVT, not NVE.
Yes.
So energy is changing, but for all pictures here the NVT is same, NVT is same, NVT is
With
same.
respect to NVT is microstate.
Now the macrostate is defined by NVT, not NVE. That was for microcanonical picture, isolated system. So microcanonical ensemble is ensemble of isolated system for which NV is fixed for each and every microstate. But in case of canonical ensemble, you are having ensemble of a huge number of closed system. Closed system means it has constant N, V, and T. That's the thing. And now when it is a grand canonical ensemble, then this N is also being
Mu
changed.
VT.
Huh. So, hmm. So now N can be changed. N is also can be, oh, I should write it in a different way. Different. So when it's a open system, means energy can be exchanged also, number of particle can be exchanged. So it's an open system. So it is N. N is not now fixed. Mu, V, and T will be fixed. T is anyway fixed, and you know, and N is fixed means the chemical potential will not be changed. Okay, as long as chemical potential fixed, then N is exchanging with the surrounding, right? That is important. N is exchanging with the surrounding. Here, E was exchanging so that T remain constant. Here, N is exchanging so that mu remain constant. That's the thing. So chemical potential will not be changed. It will be connected. Here it was connected to a heat bath, but for grand canonical ensemble, it will be connected. You can understand with some other reservoir by which the particle is exchanging. That's it. So that the chemical potential remain constant.
For a open container.
Open container. Just you have a coffee mug. But in coffee mug, what happens after equilibrated? You can think, not coffee mug, beaker of water, just open it. Then the particle is also exchanging, energy is being also exchanged. Okay. So now the part these walls are rigid and not rigid. It's thermal conduct, thermal conducting, heat conducting, and also permeable, so that the particles can be exchanged between these walls. Okay.
The number of particle escape from higher chemical potential to lower chemical potential.
Yes.
So
But
why it
chemical
is,
potential is same. Chemical potential is not changing. Chemical potential is same.
it is the escaping tendency of matter?
No, 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 no. It's like that. But first understand for NVT, energy was previously energy was fixed for microcanonical. Now energy is being exchanged so that the temperature is fixed. Temperature of the all copies should be fixed. That's the thing. So
Yes.
to make the temperature fixed, it should be exchange energy.
To make the chemical potential fix, I should change the number of
The
particles.
particle. You just think like the two systems are there. That first temperatures T1 and T2. When they will exchange energy, then it will be T and T. Like that. It will be manipulated. Okay.
Yes.
Okay. Okay, just 1 minute. What? Okay, so let me summarize this part. It's not just thinking, it's not very difficult actually. It's when it's isolated system, nothing is exchanged. So NV will be constant. Okay. But when the it's exchanging the energy, the system is a open closed system, then obviously the temperature is constant because it's you have a system which is thermal equilibrium with the surrounding has a temperature T, so it must be at the temperature T. Okay. But energy can be exchanged now. It's a open system, you just understand. There will be exchange of energy. Is it understandable or not?
Yes.
Okay, why this exchange of energy is there? Because the walls are now heat conducting. It can exchange the energy, but you have to keep in mind temperature should not be changed. You can exchange the energy, but you have to keep constant the temperature like that. This is the constant. You can think like that. This is the constant. So you can. That's why I'm saying you can think like that. In initial, it all has a different energy. That's why it has N, V, T, all are same, but energetically it may be one, it may be two, it may be three, it may be again one, it may be five, it may be four, maybe six, it in E2 again. So you will have different number of energy of the macro state will be different. That is the thing. Or you can think like you have to make copies of NVT system. You can make copies with different energy. That's the case. When the energies are different, then energy will be exchanged between them. That is the reason.
So how can temperature be constant and the energy be different?
How can energy, you can think like this energy of these two macro states are different, but I am saying the temperature is constant. That's the question, na?
Yeah,
So
yeah.
it's quite tricky actually. This energy is entire energy, just you have to understand. It's not the kinetic energy only. Temperature is only governed by the kinetic energy. If you remember kinetic theory of gases, the kinetic energy, from kinetic energy you only get the temperature, but there are other energies as well. Potential energy, magnetic energy. So
Vibration energy.
there are various type of energy, but this energy is internal energy, E. So E it will include all types of energy, correct?
Total energy added up in all form.
Total energy added in all forms. So maybe kinetic energy is fixed, but other energy may be different, na? That's the reason. Do you get it?
Yes, yes.
Yes. So when it's exchanging energy, it may be, let's say some energy goes outside. So, but kinetic energy should not be changed. Then temperature will be changed. That's the case. Okay. Okay. So here also, mu is, what is mu? Mu is G by N. Gives free energy by number of
Partial
particles.
molar gives free energy.
Gives free energy by particle, number of particles. So particle is changing, but so that overall mu can be constant. G is also changing. So that's why mu remains constant. Mu can't be different. That's the case. Okay. Just think it. Otherwise,
So
you
if
will.
n changes, the g also changes, but the ratio keeps same.
Yes, mu remains constant, right? That's the thing. Uh, for same potential, both are. Let's say you have a system and it is interacting with surrounding. So let's say the chemical potential of surrounding is high and it's low, then particle will come inside. So particle is changing, but chemical potential is not changing. That's the reason, no? Because when particle is coming in, n is increasing, but g will also increase. So again, it will be same like that. It's not very trivial. I'm saying how this npt and upt is becoming constant. Just you have to think it. Just think it. If again there will be doubt, I will again explain it. Okay. So, but there are other types of ensemble as well. One is called isobaric isothermal ensemble. So from nomenclature, it's clear. It's isobaric means pressure is constant, number and temperature. T and T is fixed, and this is very useful in our day-to-day life in laboratory or anywhere laboratory. P and T is constant basically. Temperature is anyway constant. You are not heating anything in that case only. It's not a chemical reaction. Then P is constant because atmospheric pressure is constant, atmospheric temperature is more or less constant, and number of particles is constant. So P and T is very useful ensemble. It's called isobaric isothermal ensemble. Okay, so these things is there. Okay. Huh. Now this is, I think this is understandable. Let me write it in a fresh notation. So there are three type of ensembles. One is microcanonical, that is an ensemble of isolated system. So N, V, E are the constant. Next one is our canonical ensemble. This is ensemble of closed systems. So NVT is constant. Another one is grand canonical. This is ensemble of open system where mu VT is constant. Mainly these three. Okay. So next thing we'll discuss the thermodynamic limit. As I mentioned before. Question. Here I have drawn these figures before. Okay, it's understandable. So what does it mean? Five thermodynamic limit. This is not very difficult. You just explain it. So let's say this is your macroscopic system. Okay. So you know for this macroscopic system how to deal with the thermodynamical property like entropy, enthalpy, internal energy, these things, right? You know the
Yes.
equations, you can calculate. You can't calculate the exact values, but you can calculate the differences.
Change of
Basic
the two system.
two properties. These things you know. So basically, for if you look at the macroscopic system, for macroscopic system, n is very large. It's around 10 to the power 23 if it is 1 mole, and volume is also very large compared to a molecule. Both are very large. But importantly, NV is not infinite, it is finite. N by V is finite. Okay, so this is important. NV should be finite. So if you from here, this is called thermodynamic limit actually. Thermodynamics works when this N by V is finite. Otherwise, you can't apply thermodynamics. Thermodynamics is not applicable. Okay, as long as N by V is
It doesn't
finite,
have to be constant, but it has to be finite, right?
it's not has to be constant. It should be finite.
Okay.
So essentially, there will be if you plot N and V. Sorry, it should not be like this. It should be like this. N and V. So when both you can classify four regions like this. This part I did. Okay, you were not there. Okay, so four regions where in this region both N and V both are infinite. You can think like that in that region. So in this region it is thermodynamic work. For these regions also when both are close to zero, tends to zero, then also it works. But problem is with these two regions when n is zero but v is infinite, then or when n is
N is
infinite,
infinite, V is 0.
v tends to zero. In these two parts, you can't apply thermodynamics because here if n by v in this point n by v is zero, tends to zero. It's not a finite thing. Finite does not mean always infinite. Finite means it's a quite reasonable number. If it is 10 to the power minus 25, that is also not finite thing. Okay, and
Where
it is,
both are infinite, how can it be finite?
let's say one is 10 to the power 23, another is 10 to the power 21. So is
No,
it
it's
finite or not?
infinity by infinity, indeterminate.
Not like that. Infinity means infinity is a number, right? Infinity is here for our macroscopic system. Both you are not, you can't do it like mathematically. Infinity by infinity, it's indeterminate. Not like that. Infinity means a huge number, large number. V is also a large number. When you divide both large number, then you will have a reasonable
Yes, then
number,
a finite quantity.
finite quantity. That's in that way. Okay. So in this region, thermodynamics works, and this thermodynamics is known to us, that is called classical thermodynamics. We always, but while doing classical thermodynamics, we don't focus in the structural orientation, means statistics of the molecules. So that's why you have to understand the statistical. So when you look at this classical thermodynamics from molecular perspective, then you will have the statistical therm.
Where
That is
n and v tends to 0.
energy tends to zero.
No, n and v tends to 0 for one
I'm
molecule.
coming. I'm coming. I'm coming. So this is called statistical thermodynamics. When actually you are implementing statistical mechanics, statistics to calculating the thermodynamical property that I have already discussed in last class. That is called
For individual
statistical
molecules.
thermodynamics. Huh. But here, when n and v both tends to zero, you can't consider particle as a classical particle because your number of particle is very small, your volume is very small. You have to consider the particle quantum nature of the particle. Okay, so you have to consider the quantum nature of the particle. So essentially you have
Particle
to
means
do,
the gas molecules.
yes,
The electrons are quantum particle,
elect electrons are quantum particle.
but the gas molecules are classical.
If you choose the gas molecule, obviously, if you choose the gas molecule, for gas molecule, when n tends to 0, v tends to 0, what will you calculate? Then the
So we can have a small system with small number of particles and a big system with big number of particles, but we can have an empty
no,
system,
but
right?
small system is, let's say you have 10 molecules and in a very small v, then the quantum natures will be significant because molecules are also made of electron, protons, these quantum natures, right? Then quantum natures will be significant. In solar cell, if you know that is molecules, but molecules behave like a quantum dot. These things will appear always. You can't
In
neglect the
solar panel,
huh?
in solar molecule behave like quantum.
Solar cell. We use the molecules. But actually, you are correct. There is not clear distinction between when the classical mechanics will work, when the quantum mechanics work. That is not even today. It's not very clear. For two different domain, we use different mechanics, but it should not be because when you just becoming from microscopic world to macroscopic world, at extreme of macroscopic world, you know the classical mechanics will be sufficient. You know when it is macroscopic world. Uh, just you think now, in a microscopic world you have a particle, just one particle, then you can't implement the classical laws. Quantum nature will be there, quantum features will be appearing. But if you impose that condition,
Oh,
you will choose the particle as a classical particle, then it's a different thing. Because when v tends to 0, then automatically you have to consider the quantum particle by default. That's the reason. N tends to 0 means in this domain you are considering with few electrons, like that. Particle is way bigger than molecule is way bigger than electron. These things you can think like a quantum dot, quantum wire, nano wire, like this, where V tends to 0 and electron is moving like that. Then the number of particle is also very less and V is also very less. So quantum thermodynamics you have to do. But if you impose that, okay, no particles are classical particle, then obviously, then no. You have to do classical thermodynamics, nothing now. That's correct. Okay, I think this is understandable. But
Yes.
these two domain, you can't do anything. No thermodynamics can be done here. Can't do it. Because you see, volume is large and particle number is tends to 0. Volume is large means you can think like a classical volume, and particle, no particle, one two particle is there. So no thermodynamics will be there. It's not that you can't do, there will be no thermodynamics even. You have a beaker, and in beaker you have put one molecule. You will see any thermodynamics? Nothing, right?
Yes.
Similarly,
Yes.
volume tends to 0 and you have huge number of particles. So what does it mean? It does not mean anything actually.
What is the example of it?
That's just, you can consider electron gas. Electron gas is confined. Electron is anyway very small particle, so huge number of electron is there. So there will be also no thermodynamics. The volume is tends to 0, but there may be any other phenomena will be there that I actually don't know. But not only this is very interesting thing to discover. Even these two parts. That's why this called thermodynamic limit n by v should be finite. Let me read it the proper words. What is the actual definition written in the book? That let me see.
Every thermodynamics is under this limit.
Huh?
Statistical, non-equilibrium thermodynamics.
Everything. Statistical thermodynamics is not a different thermodynamics. It's a way of looking. Statistical
Yes.
thermodynamics is just looking from molecular point of view, just by using the statistics of molecular distribution, and you are calculating using statistical mechanics that thermodynamical property. That is the statistical thermodynamics. So here it is written n tends to v, n tends to infinity, v tends to infinity, so that the density n by v that remain finite. These are called thermodynamic limit. In thermodynamic limit, the separation between energy levels are so small that energy may be regarded almost continuous. That's the case. Okay, so it's correct. Now, okay, I think it's enough to say with thermodynamic limit. Okay, so now we have to go with the canonical ensemble. But should we go today because it's already, because canonical ensemble will. What do you want? Should I discuss canonical ensemble in detail or just uh, partition function and then calculating the properties?
In details.
I think it's better because now you can understand that this thing. When you understand the canonical ensemble, then everything will be very clear. After doing canonical ensemble, you can easily do the grand canonical one. But for micro canonical, you don't have to study anything for micro. Oh, okay. Oh, you don't know the partition function. Otherwise, I would say. Um, what will be the, let's say, I'm just asking, if it is a micro canonical ensemble, what will be the this omega number of microstate? What will be the probability probability of having a microstate? What will be the probability of having a microstate? This omega
All
is the
microstates will be equal
having
in
a one
probability.
microstate. This is a huge collection of microstate, right? Huge collection of
1 by
microstate.
infinity.
1 by omega,
Infinite.
not infinity, omega. Omega is the number of microstate here. And that tends to infinity, you
If
are
omega
correct.
is
But here
finite,
I am saying this is the number of microstate. So pi will be 1 by omega. Just you put it that our formula na kb, sorry, that what was the formula, that s was uh,
k
pi
minus kb, summation
ln
pi,
pi.
ln pi.
So now if you put it, so what will be p? probability
1 by omega.
1 by omega, and it is ln 1 by omega, and it is sum. Sum means n, because for all cases probability is same. All system are NB, NB, NB. Just you have to multiply it with n, and there is a kb. Okay, minus kb was there. Sorry. So it is minus kb n by omega ln omega, and minus will be these things. Okay. What is n? Just okay. Let me put
Avogadro
k.
number.
No, 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 no. Just do it. Let me do it. kb sum over I rho pi ln pi. Is clear? What is I?
In ith state.
Ith state, ith microscopic state, right? Then
Yes.
you have to sum over all microscopic states. So it should be 1 to omega, because you have omega number of microscopic state.
Yes.
So it will be minus kb sum over I 1 to omega. It is 1 by omega ln 1 by omega. Correct?
Yes.
Probability is 1 by omega. And you have omega number of state. So for all cases, this is same. So this you have to just add up omega times. So it is just multiplied with omega. So omega omega cancels. It becomes kb. Then this is the entropy. But when Boltzmann gives this formula, Boltzmann gives just this. He did not know from where it came. Nothing. He just feel it that entropy must be related to the number of microstate. It must be. From that picture, he just gave the okay. Then, but he just entropy has a unit, and omega just is a number of microstate. To make the unit match, he just put kb, a constant. Later, it was measured in terms of name in terms of in name of Boltzmann. It's called Boltzmann constant. But but people did not knew which is what is the value of k. When using the statistical properties, statistical mechanics, you will calculate, you will derive the formulas for our ideal gas or anything. Then you will figure it out that okay, this kb is nothing but r, r by n. N is the Avogadro number.
Yes.
That will when we do canonical ensemble, you will see in canonical ensemble also it will be just kb. One constant will be there. You don't know whether that is Boltzmann constant or not. But when you measure the this ideal gas equation from these formulas, these statistical mechanics, then you will figure out okay, this kb is nothing but this r by n. From there you will have this. Okay. Okay, so I think for today it's okay. In next class we'll totally discuss the canonical ensemble, and also in this week the sir was also saying that the canonical ensemble will be taught right in this week. So I'll totally focus on canonical ensemble, and then again I will ask you whether any doubt regarding. Then I think overall picture, microdynamical, these things, I thermodynamically everything will be more clear. Then if you have any doubt, you can again say. First canonical ensemble we have to discuss. It will be
Okay.
bit confusing. It will be bit confusing, but I will try. I will try. And it is quite mathematical also. I don't know whether in one class it will be covered or not. I will try. Just I have to go through the partition function. You know the partition function, but
Yes.
we have to derive it, partition function. When you after knowing, as like in quantum mechanics, if you know the wave function, you can do anything. Just for different ensemble, different cases, you have to just calculate the partition function, and you using that partition function, you can calculate any thermodynamic property. That's the motto. Okay.
Which mathematics are needed?
Which mathematics are needed? Mathematics, all that x average is xi sum over xi pi, that I have said na yesterday.
Statistics only.
Uh-huh. This is the main formula. You have to just calculate pi. You know na, this pi will calculate that e to the power minus beta ej divided by partition function q.
Yes.
Just put it, and q is actually sum over e to the power minus beta ej. These things we will calculate. How these things appearing, and then automatically you just put it here, you will calculate the x average. If it is internal energy, it will be EIPI. It will, if it is enthalpy, HIPI. If it is entropy, SIPI. Just like that. Thus, we have to derive this formula with expression, how it's coming. So for microcanonical ensemble, there is no distribution. That's why it's very straightforward. All have the same now. No distribution is there. All have same energy, same number of particles, same volume. In canonical ensemble, you will have a distribution in terms of energy. All does not have the same energy. You need a statistical distribution. Then only you can do statistics. Correct?
Yes.
But how we can do the this microorganism ensemble? If I want to write the distribution, how we can write? It's just a delta function, e minus h, something like that. Only one is allowed, other for all e it is zero. Probability
Oh,
if
so
I want
this probability is equal to 1 by omega only works in microcanonical.
only. That's why this formula is only for microcanonical, not in general.
Ah, okay.
But this is general formula. Later gave this formula. Okay. Okay, so let me stop here today, and again in next week we'll meet, and just watch the lectures video, and if you have any doubt you can again ask me in next class, or you can ask me in WhatsApp. So I think I have you have my WhatsApp number. I have shared yesterday in last class, so you can ask me there also.
No, I was not there in the last class.
Oh, okay. So this is my okay. So you can if you have any doubt you can ask me. And this from which notes, from my MSc note I will teach this canonical ensemble, and I will share that after, because it's you don't need to read all things because it's quite it's more advanced things, but okay, but canonical part is there. I will discuss from this note entirely. So these things I will discuss next time, and after that I will upload these notes in the Google Sheet, Google Drive, and I will share the link. Okay, okay. So now I think I I can stop sharing. Okay. Okay, so for today, so okay, thank you for joining. Again, we'll meet in the next week from 4 p.m. and we'll do it. If you have any doubt, you can ask me. I'm not sure that I will capable for answering that or not, but I will try. Okay, okay. Thank you. So let
Thank you, sir.